Hello, everyone. My name is Kamil Bogacz. I'm a solution architect here at AWS. And I'm very happy to bring this session to you, in which we hope we're going to put you on the path from the conceptual understanding of edge compute solution in Amazon CloudFront to the level of practitioner of those technologies. And I do get it. This is quite a bold statement, right? We all know that this is the path that leads through a lot of practice, lots of experimentation, hands-on experience. But I do also believe that taking the time to go over some proven use cases, unpack some of the best practices, look closely into some of those nuances, dependencies, will help you in building the right mental model to navigate that path. So to that end, I also have with me two other fellow practitioners on my right, David Brown, Principal Product Manager on Amazon CloudFront, and Danny Turgeman from AppsFlyer, Vice President of R&D, who represents one of our customers who use those edge compute services extensively. And now, before we go on, I need to make sure we are perfectly clear on one thing, and that is what type of edge compute we are talking about even. If you look it up in the content catalog and you type in edge, you're probably going to find a lot of sessions that relate to different technologies, different industries. So let's be clear what we are talking about today. So the edge that is our focus refers to AWS Global Edge Infrastructure with Amazon CloudFront as a core service, with edge compute options that enable you to run your own code on top of that infrastructure to customize content delivery for your web applications. All right, so now that we established what flavor of edge we're going to be talking about, let me give you a quick rundown of the agenda. So we'll begin with doing a bit of a recap of what edge compute options are available. And we're going to put a lot of emphasis on how do they fit into CloudFront workflow. And this is really important because CloudFront sets the whole context. It's the source of all the dependencies. And from my experience, it's only when you get the solid understanding of those, you would be able to make informed decisions about your own implementation of edge compute solutions in your architecture. And then we'll walk through some of the proven use cases that illustrates well what type of problems you can solve by running your code at the edge and what makes it a good idea in the first place. And last, we'll hear from David, who will swipe through some of the best practices that will help you to improve the performance, scale, but also to better manage the service limits. All right, so early on, I made the statement that edge as a term can be associated with many different technologies. And those pertain to different use cases, different industries. But for all of those technologies, what is really a defining trait is the underlying platform. Because that platform is what determines later on what's the deployment model, what's the capacity you have at your disposal, and then what are the capabilities that you can use. So for the topic of this session, that brings us to Amazon CloudFront, which is AWS Content Delivery Network, improving web application delivery for customers across all industries at the global scale. And that scale factor is something that we attribute to AWS Edge Network, which is a global infrastructure built specifically to reduce latencies and add more resiliency into your workloads. Now, what makes it possible is a constantly growing footprint of edge locations, and now we have more than 700 of them, which are filled with CloudFront hosts, serving your traffic into the local viewer networks. Now, all those edge locations are also very well connected with any AWS-hosted origin. And that happens through AWS Backbone Network, which ensures stable, high bandwidth, and redundant connectivity all the way from those AWS regions to those edge locations, making it also isolated from any internet-level instabilities. Now, the first component that also extends CloudFront reach deeper into ISP's network is made of more than 1,100 embed POPs, which are just small deployments of CloudFront installed deeply into ISP network, which also bring your content even closer to the viewers that we are trying to reach. Now, switching back from that physical to logical topology view, you should also know that CloudFront is hierarchical by design. And this is to balance the growing scale of the edge infrastructure with the load that it puts on the application origin servers. And just to give you a perspective, in the last 2 years, we have grown from 400 to 700 locations. And if you think about it, this is definitely a good thing, right? We want to grow our infrastructure to serve more traffic locally and also reduce latencies, especially when we install the new POPs in the new locations. However, the side effect of all of that growth is that the increased number of edge locations also generate more aggregated load towards the origin. So to mitigate that, CloudFront introduced mid-tier layer of 13 regional edge caches that act as a parent caches to all of those edge locations. And their job is to basically absorb all that load from the nearby edge locations and also minimize the load they put themselves on the origin because, after all, we need to fetch the content from your servers. And all of that introduction leads us to the core idea that drove the invention of edge computing. And that is, hey, why won't we use all of that compute available in all of those locations and dedicate some part of it to run customer logic, to run customer code? And so we've been pursuing that idea for many years now, and we have well-balanced portfolio of edge compute options. And how we make this compute available to you today? Well, there are two options, and if we look at it again from the infrastructure point of view, at the level of all of those 700 edge locations, you can run your code in the form of CloudFront functions, which allows you to execute short-lived, lightweight functions as close to the viewers as it possibly can be. Now, complementary to that feature, you can also associate your function with a key value store, allowing you to decouple the application data from the application logic, but still push all of that application data to the same edge locations, making them instantly available to the code itself. Now, the other option exists at the level of regional edge cache locations, and that's where you can use Lambda at the edge, which is basically CloudFront extension of the Lambda service, so if you ever use Lambda, which is the Lighthouse serverless service of AWS, you can expect similar developer experience in terms of developing the code, operating it. But what makes it unique with Lambda at the edge is that we take care of replicating that code to all of the 13 regional edge cache locations. Now, in contrast to CloudFront function, Lambda at the edge supports more complex logic, which requires often longer execution time, maybe network calls to the third-party API, and also adding some third-party libraries as well. All right, so now, as we added edge compute into the picture, that also means that we are dealing with serverless model, which is predominantly event-based execution paradigm, in which any function is invoked in response to some event trigger. Now, putting that in a CloudFront context, all the event triggers are associated strictly with the request and response flow in a single transaction that takes place between the viewers and your application that you host on CloudFront. More specifically, CloudFront defines 4 event triggers representing different steps in that request-response flow. And so we have request path with viewer request, which corresponds to one of the first steps in request processing after CloudFront received the request from the viewer. And now, important thing to remember is that this step happens before the cache key is even calculated. On the opposite end of that path, we have origin request path, which invokes the code just before the request is forwarded to the origin. And that also implies that this trigger is invoked only after the cache miss happens. Now, switching directions on the response path, the order is reversed, as you may expect. And we have origin response logic, which intercepts the response from the origin right after early on when it's received. Then we have also viewer response, which is triggered just before the response is dispatched to the viewer. And so, as you may imagine, all of those event triggers, they also strongly determine what type of use cases are applicable for each of them. There are some nuances you should also know about those event triggers. Specifically, remember that for the origin-facing triggers, these are only available for Lambda at the edge use. For the viewer-facing trigger, you can use both, either CloudFront function or Lambda at the edge, but remember that you cannot mix both. So if you have your solution requires you to use both of those response triggers, then remember you have to stick with one option as you go forward. Okay, so concluding what we have learned so far, there are some decisions to be made, right? You have to select the event trigger, you have to decide between CloudFront function or Lambda at the edge. As you know, those decisions will have really important impact down the line on the performance, scale, and the cost profile of your solution. And what I always suggest that a good place to start is to have a look at the service limits for each of the two options. And I know that scrutinizing the specs is not the most exciting thing you do during the design process, but I also believe that those limits really speak to the type of use cases that each option is best suited for. So I'll put a pin here because David will talk about the limits later on. All right, so limits is just one area of consideration, but the second and probably even more important one is what actions your function can drive. And I'm not talking here specifically about what you can do in the code itself, but how the output of your function actually determines the next step that CloudFront will take. So that brings us to the function lifecycle, and let's examine that more closely. So when the function is invoked, it receives as an input either request or response event, depending on the direction of the path. So for the request path, this is basically event object, which details all the properties of the request. So headers, query string, cookies. When you slam that at the edge, you can even access body of the request. Now for the response event, as you may expect, you can see and inspect what are the response attributes, so the status code and the headers as well. What might be less obvious is that also on the response event, you will be able to tap into the request details as well, the same request that took a part in the same transaction. And this becomes very handy quality when your use case depends not just on what your origin response, but also what was the request that led to that response. All right, so in a typical function lifecycle, you get those inputs, your code does its thing, and as any function, it needs to return something, it needs to return an output. And actually, CloudFront awaits for that output before it can move forward with the request or the response. So there are two types of outputs that your function can generate. So the first one is you can return a request, that input request or response event, and then when CloudFront receives that, it will just follow along according to its normal and standard workflow. So when this option gets exciting is when you realize that any changes you made to that event response or event request object will be actually reflected in the underlying request or the object. And this is one of the main power of edge compute in CloudFront, that it allows you to modify requests and responses on the fly. Now, where it gets even more exciting is that on the request path, the request event also includes the origin object, which outlines what is the origin that this request should be routed to according to the CloudFront configuration. And in the exact same way, on the fly, you can also change the direction and by overriding the domain name, which will make the request to be sent to any origin that you specify in your function. Now, the second option is that rather returning response or return event, that you generate your custom response in the function, and that will make CloudFront generate the HTTP response accordingly and send it straight back to the viewer. Now, depending on which trigger apply this action, the implications will be different. So on the request path, that will mean that basically the underlying request will be terminated, and it won't be processed any further. Definitely, it won't go up to the origin. Now, if you return that response on any of the origin-facing trigger, that response will be also eligible for caching. And this is also very helpful quality because it allows you to generate that response only once from the function, store it in cache, and make it reusable for any subsequent request. All right, now having that deeper understanding of edge functions, their capabilities and dynamics with CloudFront, we are in much better position to identify the right problems that can be solved with edge functions. So I pulled together all of those use cases. I also grouped them per specific event triggers, which have proven to be the right fit for purpose for the most part. So starting with the request path on the top, you will often find that for a lot of those use cases, view request is the only sensible choice, really. And this is because for a lot of use cases, what matters the most is the ability to pre-process the request before that request even hits the cache. If we take access control, for example, right, you have very strict order of action that needs to happen. So if there's any unauthorized request, you need to block that request before that even reaches the cache. So if you are not able to stick to that order, then you cannot even put that protected content in a cache. For the next three use cases, what matters the most is the ability to change those attributes on the fly, as we said on the previous slide. And especially those attributes which are part of the cache key. Because that ability to count the cache key from the function, for example, allows you to achieve better cacheability of your responses. It also allows you to segment your audience and then transparently point them to the version of the object optimized for a specific group. Now, response rendering use case is what we talk about, is when you covers all those use cases where you terminate an underlying request and you generate your own response. And depending on the use case, depending on the requirements, sometimes origin request turns out to be a better option than the viewer request, especially, as we also said before, if that response can be put in cache and reused frequently by the others. And that leads us to the final use case on this path, which is origin routing, which basically gives you the ability to define more advanced origin selection patterns beyond the native one that CloudFront provides, which is purely path pattern based. And that use case used to belong exclusively to origin routing, but if you have been tracking the recent announcement, you should know that it's now also possible to change the origin on the fly with the CloudFront function. And on the response path, a lot of the use cases really revolve around the compensating for the missing logic at the origin. So if you're having some kind of third-party CMS, for example, sometimes you don't have the full control over what status codes or headers are being returned. So typical action on this path is, for example, is to add cache control headers, is to add some security headers, or things like that. Very often, function on the response path is complementary to the logic on the request path. So for example, assuring session stickiness in a variant selection use case. In order to do so, very often you would set a cookie which assures that session stickiness. All right, so enough of the theory. Now let's put all of this to work. And let's start with a simple scenario, and let's assume that we are running a news website. The architecture is as simple as it possibly can get. And so we are publishing the articles through some third-party CMS. Then we have, of course, CloudFront responsible for delivery and making sure the performance is in check. And on the origin side, we are also hosting image transformation endpoints, which optimize images for the format and the resolution based on the image request parameters that came in. And now let's say we are in the middle of our annual planning process, and we set out the plan for next year with the key initiatives that we want to work on. And this is the plan. So first, we want to solve the problem of the abusive actors DDoSing image transformation endpoints. And the way they do that, they scramble the cache. So they send a request float with the randomized inputs that leads to the increase of the cache misses, that puts higher load on the origin, eventually leading to the service disruption. The second one comes from the business who wants to introduce subscription-based services. And in technical terms, that translates into setting up a paywall. The third one, again coming from the business, is to provide better way to run the experiments, such as A/B testing, through a simple interface that the product teams can use to define the experiments and initiate them. And the fourth and the last one is, finally, we need to get sorted our SEO rank. And we knew for a while that our poor rank was what was partially responsible was the raw URL format dictated by the CMS that we are using. So we want to introduce user-friendly URLs because we know for a fact that search engines highly rank on more descriptive URLs. So let's address those requirements one by one. Start with shielding our image transformation endpoint from all those malformed requests. If we think about this attack vector more carefully, we'll find that actually what the attackers are exploiting is the fact that we have no safeguards around the attributes that constitute the cache key. So that what allows them to effectively bypass the cache and hit the origin. And so we know what to do in this case, right? We need to apply cache normalization. And that leads us to viewer request trigger and CloudFront function, because this is rather straightforward and self-contained logic. So in the function code, what we need to do is basically list all the discrete values, which are typical inputs for resolution inputs for various screen sizes. And then when a request comes in with some unusual value, the function can basically override it with the closest match in that list. And as a result, we restrict the number of possible cache key variation, and this is exactly what we wanted because that takes care of the problem of scrambling the cache. Now, looking at the rest of the requirements, adding paywall basically translates to adding access control methods. And this is something that our customers very often bring up with us, and they usually decide on implementing token-based authorization. So in this approach, it is assumed that any authorized client holds on to the cryptographically signed token. And then our function needs to play a role of a gatekeeper and validate that token, make sure that the signatures are right, and also that any access condition in that token are met, such as making sure that the viewer request is coming from the viewer country or viewer ASN to which that token is restricted to. Now, tokenization is a good solution. It's not the perfect solution, and it's still possible that some of those tokens can be leaked. But you can also respond to that. And simply by running some outlier analysis of the access logs of CloudFront, you can identify which of the tokens and associated accounts have been compromised, push those accounts into so-called revocation list, stored in a key value store, and then when someone tries to reuse the same token again, the function will basically look up if the associated account is on that list and block such a request, if so. Now, let's not forget about our SEO crawlers. Now that we introduced token-based access control, obviously SEO crawlers won't be able to authorize themselves and present any token. And so we need to make exception for them, and this is where AWS WAF comes to rescue with its bot control solution. The bot control solution is capable of identifying SEO bot traffic, making sure this is not spoof traffic, and also mark that traffic with the appropriate secret header that we can pick up in our function, and then knowing that this is traffic coming and this is verified traffic from the SEO crawlers, make an exception and skip the token validation step. Now, when it comes to the use case of introducing page variants, or friendly URLs, this is a perfect use case for the key value store, which can now become the simple interface for our product teams who can push page configuration into key value store, and then when the page request comes in, the function will read that configuration, and it will immediately know how to translate that user-friendly URL into the original URL that our CMS would be able to understand. And if any A/B testing, any variant testing has been configured, the function will also roll a dice and decide which variant of the page should be served to the viewer. And so as the viewer request function makes that decision which variant should be served, we also want the viewer obviously to stay on that version for a little bit. We don't want the viewer to constantly switch between the versions when they navigate back or they reload the page. And so for our variant selection use case, we need to expand that logic to the viewer response as well and implement some form of session stickiness. And the simplest way to do so is to basically add a cookie. And so we are adding our viewer response function, which does exactly that. It sets a cookie with a specific value that determines what's the version of the page that the viewer should stick to. And then if you remember from the previous slide, the viewer request function then looks for that specific cookie. And if that cookie is present, rather than rolling the dice again, it will send the viewer straight to the target version of the page. And now if you're wondering, hey, how can viewer response function knew what was the initial result of rolling the dice, then I'm just going to remind you that the viewer response event trigger also specifies the details of the request involved in that same transaction. So from the viewer response point of view, you can see the effects of running your viewer request function. And this is what we take advantage of. All right, I hope this hypothetical but realistic scenario gave you a good warm-up to hear about real-world scenario from AppsFlyer, and most importantly, what tangible result they were able to get.
Okay. First of all, thank you, Camille and David, for the opportunity to present AppsFlyer use cases in this pretty important topic. I must be honest, this is my first time in an event, my first time on stage. You can hear my heart beating from the excitement. I'm Danny. I'm a leader engineering from AppsFlyer, responsible for several development groups, mainly the groups that are handling all the incoming data, all the ingress data, processing them, responsible for replying back to the end users, doing the attribution, our main business core, and also sending the data out to different kind of channels, can be partners, can be customers, but mainly to downstream consumers that are taking the data and building all our products on top of that data. For those that are not really familiar with AppsFlyer, I will not deep dive to any marketing details. I will try to simplify what we are doing. We are a digital platform that measure the effectiveness of the campaigns, the marketing campaigns that are running on different kind of channels. When I'm saying channels, any channels that you are familiar with. It can be Meta, it can be Google, it can be Amazon, it can be TikTok, Snap, anyone that you know, we are there. We practically measure how user interact with the user. And from that point, what he's doing, it can be install of the app, it can be uninstall, it can be any significant in-app, any significant action that the app owner or those that have behalf of the app owner want to measure in order to increase the ROI that the user brings to the app. Now, you can look on your mobile. You can see many apps. Most of the chances that AppsFlyer SDK is in your app more than one time, which leads me to the footprint on AppsFlyer. We are appearing on a billion of devices around the world. And why it's important to me to mention that, because we are talking about edge computing, so the resilience of the data and how we expecting for Amazon for AWS to receive this data is very important. Usually takeaway are taken by end of the session. With your permission, I would like to start from the end. What is important for me that you will remember will take from my 14 last minutes that I have to present to you. First of all, one second. Yeah. First of all, is really the strength of the value of that computing and how really AppsFlyer is leverage it. Secondly, the fact that it's decoupled from our architecture. By the way, we migrated most of our data, 95% of the incoming data. We migrated to another cloud provider, to the CloudFront, the CDN, last June in around 1.5 months. Basically, we didn't change anything in architecture. We leverage the edge computing capabilities that enable us to really to serve our business. And the last thing that we are not doing it because AWS beautifies. We are doing it because it's bringing value to our business. When it's bringing value to our business, our customers are happy. When customers are happy, apps are happy, and I'm happy also. So those are the three that I will support now using my use cases that I'm planning to present. Usually when saying AppsLayer, it's production. It's an equivalent word, and production speaks volumes in AppsLayer. I want to just emphasize the numbers because it's really important to show a little bit the context of the numbers. I will not really show now here numbers of all the system. Portion of this system, part of the ingress components. You can see here the data is huge. We have around 220 impressions per day. Impression is a view of ads. A little bit less of clicks and events. Approximately, it gives us 2.5, 2.6 million requests per second. It's a live kicking environment. Production is a big issue in AppsLayer. So those are the numbers. It's important to me to say that because we are talking on the edge, I want to emphasize that. Let's drill down a little bit on the ingress high-level architecture. Data is arriving from different kind of platforms. It can be arriving from devices, different kind of devices, TV, consoles, servers, doing the Route 53, the DNS resolving, moving to the CloudFront, the CDN provider. For most of our distribution IDs, we have attached WAF. In this case, and I will show it in the second use case, we are not using it only for security reason, but also for business perspective, and I will show it, how we leverage it. Then the data moving to ALB, and from that point to the instances. The instances, I'm referring to our web handlers, the first ingresses microservices that handling the data, holding all the logic to redirect the users to the relevant stores, and downstream to other components that doing our main business. What are the use cases that I'm going to focus and show? First, user agent. What is the meaning of user agent and how we tackled client hints, what Google introduced about user agent, and how they are answering the privacy concern about it. I will show it an example. And the second, it's some collaboration between the WAF and CloudFront function and how we collaborate between them and leverage our business around origin selection. It's not just how we're retrieving the user agent, is also just how we identify who is sending this data. It can be a mobile, but it can be a server that's acting on behalf of a mobile. So let's drill down to the first use case. Any interaction, any ad interaction can be arriving from different kind of browsers, but it can be also from different kind of social apps. Practically, it's different logic to handle them, but by the end of the day, we need to retrieve the user agent from those interactions. However, until Google introduced the client hints, we received it as a traditional way on the click. We saw it on the impression, and we retrieve it. Why it's important for us, the user agent? Because we use it for two main reasons. One of them, we are doing based on the user agent, redirection the user for the store. How we know it based on different kind of data that appearing on the user agent. And the second, we're using it for the attribution, main logic to who we're giving the credit and from where user arriving. The reality, Google introduced client hints, which is another addressing concerns. There will no longer be a user agent available or partial available, and we need explicit to ask for the client, give me the missing user agent. As I mentioned before, it's crucial for our business now. Doing this kind of privacy can kill our business. So for example, if we got in the previous, in the original, before Google introduced client hint, all the data that you see in green, the Android device, the OS version, the device model, the Chrome version, that's crucial for our business. From now on, you get it partially, and you need to ask explicit to enhance the data. So I will show how we tackle it in the naive way and how we leverage it using the CloudFront function. So the draw speaks for itself. Click was sending on the mobile. It's arriving to CloudFront, ELB, and then the instances. Then, unlike before Google introduced the client hints, we are unable now to retrieve the user agent. we need to add a logic to retrieve and understand that first we have a missing user agent that is crucial for our business. In order to get that, we identify what is missing and sending back to the client what is the enhanced user agent that is missing. The client receiving that and then replying back with the enhanced user agent that is crucial for our side. Only then in point 3 that we're getting the data, only then we can act and define what is the user agent, the missing information that was crucial for our side, and then we're doing the redirection. So practically, you can see the round trip is a killer. And again, in the web endor, we need to add logic to identify that we have a missing user agent and to manage all the interaction between the client and the server. It's answer the challenge, but it's very bad because you see that we also need to manage it, and the round trip is killer. How we solve it with CloudFront function? Practically, we push forward all the logic to the edge. We still have the interaction, but it's based on the edge distribution, so it's much more closer to the user. And then as the clicks that are arriving, instead of forwarding to our web handlers, this time the function is identified that there are a missing user agent, and following that, generating a request to the client asking to enrich the user agent. And then when it's getting the enhanced, it will forward to our server. Practically, our server now acting as before Google introduced the client hit, because from first place now, they will get only enhanced user agents. So it solved the round trip, and it solved our logic to managing our servers. Really, if I would summarize it, what's it for AppsFlyer? First of all, we reduced the latency. 300 milliseconds up to 500 milliseconds reduced the latency is dramatically. It's around 30% of improving the latency. User will not abandon the flow. We bring them to the store very fast. Users are happy. Customers are happy. We are happy. And of course, from engineering standpoint, I decoupled all the logic, pushed it to the edge. I don't need really to add some complexity, which already have using redirection flow. So this is the first use case. The second use case, it's not just how we retrieve the user agent, is how we select the origin. And what does it mean? There is a very important to us to identify who sent this request. We can get it from the client with the user agent A, but we can get it from a server that's acting on behalf of a client with the same user agent. It's very important for us to identify who is the origin, because let's assume that I will not identify with the origin. I will do a redirection for a server, which is not really relevant. Let's add on top of that doing a redirection is much more compute intensive, so I will need more compute to do that. So how we identify if it's a server or a client on the same user agent? We enable query parameters that explicit mention, I need a redirection false. I'm a server side, I'm not a client. You don't really need to reply with redirection. What is the problem? That this is an optional, and enforce it to all our monetization networks and other partners, it's not really possible. So basically, the control is not in our hand. It's depend if they are declaring, I need a redirection or not. And based on that, we identify it. So actually, to process 50 million requests per minute required for us around 160 Kubernetes pods. The fact that, first of all, you can imagine we are doing redirection for those that are not really needed, and it's much more compute because it depends on the partners. How we solve that? Let's see. So first of all, I will show the example that solved that with the WAF. And the second, I will leverage it, how we did it with a collaboration between the WAF that is used for a business to CloudFront function. So data is arriving for different kind of devices, doing the Route 53, same as before. But instead of counting on the query param, we're adding a rate rule that we define what is a rate rule for server and what is a rate rule for client. We start to count it, and we tag every request with the tag based on the rate, if it's a client or server. Based on that, data is writing to the ELB. In the ELB, we added a rule that reading the header and based on that, forward it to the relevant instances. So we have several ELBs, but they're serving both server-to-server and client-to-server. Based on the rule, you know which kind of instances you need to route. It solved the problem. It solved the problem. But you can do it much more better. And how is that? Same WAF, same rule, same rate rule, same count, same tagging on every request. However, instead of moving it to the ELB and then adding a complexity of rules, do it with a CloudFront function. Cloud function read the header, and based on that, select the relevant ELB. In this time, we have different ELB for different kinds of fleet instance. And we solve the same, but without really need rules on the ELBs, but reading the header, the tag that we did with the WAF from a function and route it to ELB, and then it will arrive to the relevant instances. What in it for apps layer? Basically, of course, we offload the origin. We don't need any more this kind of Kubernetes pods because now we know who is server, who is not. And I said the redirection is much more high compute intensive. So actually, except of accuracies that we're now doing 282 servers on 301 to redirection, I don't need too much instances to serve the same amount of 50 million that 160 was before, and now 95, it's around 40% less. And of course, less compute. Happy for customers, less money, save us, of course, the cloud computing. This is the second use case. So we had two cases. First is the client hints, the user agents that save us latency mainly and simplify our engineering. The second is a combination or collaboration between WAF and Cloud Function that offloaded the origin and save us money. That's it, I think. David, it's your turn.
Thank you, Danny. Can you guys hear me? Yeah, OK. That was a great example, just to show what I like about that example is just the creativity to push logic to the edge using lots of different capabilities that we have at the edge. But the scale at which they're doing it is pretty amazing, pretty outstanding. So by way of introduction, I'm David. I'm a principal product manager on the CloudFront team. And one of the things that I hear most often from customers that are looking to leverage edge computing is, can it scale to handle my workload? Hopefully, Danny's examples here showcase that, yes, in fact, we can most likely scale to your needs. But as with any platform, there's always going to be limits, and you need to understand what those limitations are. And the better you understand them, the easier it is to understand whether we can scale for you or not. So let's walk through some of these examples here of some of the limits and what to think about. So we'll start with Lambda at edge. And there's really two limits on Lambda at edge that you need to be concerned about in terms of scaling. The first is around concurrency. And if you've used Lambda before, you're probably pretty familiar with concurrency. That's just really the number of instances that Lambda has available at any time to execute your functions. There's a maximum concurrency limit, and that concurrency limit is per region, which means every function that you run in that region counts against that concurrency limit. So if you're running both Lambda at edge and Lambda functions in the same region, those together will count against your concurrency limit in that region. There's also another limit that is probably lesser known, but has a big impact on Lambda at edge, which is requests per second or transactions per second that you can run with Lambda. That's going to be 10 times your concurrency limit in a region. So if you have 1,000 concurrency limit in a given region, that means you're going to be able to run 10,000 requests per second through that region on any Lambda function. And so you may be thinking, wait, I'm a web developer. I've got a front-end application. I know how many requests per second are coming in to my web application, but how does that actually equate to concurrency in Lambda, and how do I keep under that transactions per second limit? The equation's actually quite simple, but what you really need to understand is the average duration of your function itself. And so if we take just as a thought example, assume we have a maximum concurrency in a region of 1, which means I'm only going to have one Lambda instance available for computing. And if I assume my transaction limit is 10 times that, that means I can handle 10 requests per second. But Lambda is only going to run one function at a time in a given instance. So to get to 10 requests per second in an instance, my function needs to run at 100 milliseconds or less, right? 100 milliseconds times 10 is 1 second. So the magic number to convert between requests per second and concurrency is 100 milliseconds. If your function runs under 100 milliseconds, on average, you just take your request per second, divide it by 10, and that's going to be the amount of concurrency you're going to need. And that's going to keep you under the concurrency limit and keep you underneath the transactions per second limit on Lambda. If your function is over 100 milliseconds, you're never going to hit the transactions per second limit. You can just take your requests per second, convert your duration into seconds, multiply those together, and that's going to be the concurrency you need. So by way of an example, assume you have origin request function on your CloudFront distribution. You have 50,000 requests per second that's hitting your CloudFront distribution. In the case of an origin request function, those only run when there's a cache miss. So in this case, we'll assume we have a 92% cache hit ratio, pretty decent. That means, though, only 8% of the requests are actually going to end up on Lambda. So in that case, that's about 4,000 requests per second going to hit Lambda. Our average duration is 200 milliseconds. So that's over the 100 millisecond threshold. So to calculate the concurrency we need, we're just going to take the 4,000 times 0.2, 200 milliseconds in seconds, which is 800. Another example here, if you have a viewer request function, those are going to run on every request. So in this case, cache hit ratio doesn't really matter. Assume you have that same 50,000 requests per second coming into your application. In this case, we have a function duration of 50 milliseconds. That's under that 100 millisecond threshold. So in this case, we're going to just divide 50,000 by 10, and we're going to need 5,000 concurrency to support this application. If we jump over to CloudFront Functions, CloudFront Functions doesn't have a concurrency or a scaling limitation. It will scale to whatever traffic volume you send to it. CloudFront Functions has, however, a time limit on how long the function can actually run. And we give you a metric called compute utilization, which is essentially how long your function took as a percentage of the total time that you had to run that function. So there's a maximum allowable time. How much of that time did you actually spend executing your function? And so if you go above that threshold, your function may throttle. It may not. And so to understand how the throttling mechanism in CloudFront Functions works, we've got a nice pretty graph here that's plotting compute utilization over time. And somewhere on this graph, there's the maximum allowable time. And so you see there's a lot of function invocations that occurred that are under that maximum allowable time. But there are a couple where your compute utilization spiked to 100%, and you went over that maximum allowable time. So to determine whether we would throttle or not, CloudFront will actually calculate a simple moving average of function executions. So what we do is we take the 50 most recent invocations of the function, we calculate a simple moving average. And if that simple moving average is under your maximum allowed time, we won't throttle your function. So in this example, we had several functions that went above the maximum allowable time, but because the simple moving average stayed under it, those functions actually didn't throttle, and they ran just fine. And so as long as your simple moving average stays below the max threshold, your functions won't throttle, which is really handy. This allows you to have sporadic spikes in execution time without impacting your applications. So given there's a time limit on functions, how do you get the most out of it? How do you write functions to ensure that you stay under those limitations? So a couple of best practices here. The first one is a kind of a stylistic difference between functions and Lambda at edge. Lambda global variables are wonderful. You should use them. On CloudFront Functions, they don't work. And so what a global variable is, it's really just a variable that you set outside the context of your event handler. And the reason you would do this is just because if you reuse the function instance, you perhaps have already saved some state or some other variable that you need to use again in a subsequent invocation. But in the case of functions, they don't work. Every time you invoke a CloudFront function, it's a fresh instance. So there's no preserving state between different invocations. And so you can save a lot of space in your code, optimize your code by taking out a lot of those global variable attributes inside your code. A second best practice is around regular expression. It's very powerful. It's a great way to do string matching. But oftentimes inside your function, you're just doing pretty simple string matches. And this is an example here of just matching on a host header that's coming in. And you're just trying to see if it matches some domain name. There's a lot of built-in functions inside of JavaScript that will do that for you automatically, like this include statement here. Anytime you're going to use the native JavaScript functions, it's going to be better performance than if you try to use regular expression. And so use, whenever you can, the native capabilities of JavaScript instead of regular expression. You can use regular expression, just be judicious in how and when you use it inside your functions. This one's important. If you're using key value store, one of the things I see a lot of people doing is cramming a bunch of stuff into a single key value pair and just doing a single read inside the function, bringing that data in, and then they have to write a bunch of JSON parsing logic to get the data they want out of that big blob of config that they stuffed in there. The way that key value store works is we take the entire data set that you've provided to us and we bring it into memory inside the function sandbox itself. So when you do a read with KVS, you're essentially just reading from memory, which is really, really fast. And so oftentimes it ends up being more efficient to make multiple reads to the KVS to fetch data than it is to cram everything into a single key value store and write a bunch of complex parsing to get the data you want out of it. So if you're planning to use key value store, think about how you structure your data such that you're doing less parsing inside the function. It's going to end up giving you much better performance and a lower compute utilization. Let's talk a little bit about Lambda@Edge. So whenever you're writing a Lambda@Edge function, the first thing I always tell people to do is try it with different memory settings. Most of the time, the lowest memory setting, which is 128 megabytes, is totally fine for your use case. But sometimes paying a little bit extra gets you way better performance out of the function. And so this is an example of a function calling DynamoDB and then doing some massaging of that data inside the function. And you can see by going from 128 megabytes to 256 megabytes as the function memory allocation, I get about a 40% improvement in performance. On the cost side, I incur about a 20% increase in cost. And so you need to think through those trade-offs. Is a 40% improvement in performance worth a 20% bump in pay? Maybe, maybe not. But as you're planning your function, as you're thinking through how to leverage Lambda@Edge, make sure you take a look at different memory allocations because it may impact your price performance ratio. This one is an interesting one. One of the problems I hear a lot from customers using Lambda@Edge is around cold starts. Lambda is really efficient at reusing the same instances that you have already used for previous invocations. But sometimes we have to expand and scale out, and cold starts can be a problem. But one way you can help reduce that is to actually package all of the functions that you have on different event triggers into a single function. And so CloudFront actually, as part of the event object that it passes into a Lambda@Edge function, tells you which event trigger is actually executing. And so you can put logic inside your function to say, this is the logic to run if this is viewer request, or this is the logic to run if it's an origin request function. And the advantage of packaging it all up into a single function means that you're going to have more invocations against a single function. And when you have more invocations against a single function, you're more likely to have already had a bigger pool of warmed instances, and you're more likely to reuse instances than if you have to fan out across multiple functions. And so it's kind of a neat way to help cut down on cold starts if your function's small enough that you can kind of package it up into one. And then the last one I'll mention is just around external network calls. A lot of people use CloudFront functions, Lambda at Edge to make network calls out to various sources, databases, S3, any HTTP endpoint. A lot of times, those libraries that you're using have capabilities to ensure that you reuse connections. Again, Lambda is very good at reusing warm instances. And if you reuse a warm instance, there's a high probability that that connection's already been established and is still alive and available for you to use, as long as you tell your function to reuse connections. And so this is an example of the HTTP library. It has an option to say how long to keep a connection alive. Use that, and it will help cut down on the overhead of having to establish a TCP connection on every request. All right. So let's wrap up. So hope you enjoyed this session. We started off talking today about some different use cases with both CloudFront functions and Lambda at Edge, and when you should be thinking about using one versus the other. We also heard a great example from our friends at AppsFlyer about how to be really creative on using our edge computing solutions and how you can use it at really high scale to solve a lot of business problems. We talked a little bit about some of the limits on both the platforms and how you can work with those limits to make sure you can scale your applications properly. And then lastly, we talked about some best practices around optimizing your code to make sure you're getting the best performance out of the platforms. So thank you so much for your time today. On behalf of myself, Camille, Danny, we hope you enjoyed this session and hope you enjoy the rest of reInvent. Thank you.